So this is our last chapter for the course, chapter 6.8, which is um, exponential growth and decay. And now is certainly a really great time to be discussing this because we can take real life example from what's going on with the COVID-19. Uh, let's examine this. First, remember that our basic equation for a log function is y is equal to a0. Sorry, for an exponential function, a0, and then a to the power t, where a0 is the initial amount and a is the growth rate, and then t is the time. So um, if we consider, say, viruses can multiply at an alarming rate. Say when each virus splits or is spread to, sorry, when, what I'm trying to say here, when a virus is spread to 2 people, it doubles. And let's say if we start with only one person having a virus, which can double each day, how many will we have in 10 days, 20 days, 30 days? So our model here would be one person has the virus, the growth rate is 2 to the power t. And after 10 days, this is 1, 2 to the power 10. (1,224) people has the virus. for t equal to 10. Now, look what happens at 20 days. One times 2 to the power 20, 1,048,576 people have the virus. And by day 100, 1 times 2 to the power 100, that number will be so large that it has to be measured in scientific notation, 1.27 times 10 to the power 30. To the power 30, which is a really, really large number, 30 points, 30 zeros, or 30 places past that decimal point. So 127 and 28 zeros will be involved there. And you can actually see a graph of this happening. If I were to go ahead and say graph y is equal to 1 times 2 to the power x, and put it in fix the window from 0 days to say 100 days. And we can't really do justice to the y values here, because the y values, let's start the y values at 0 and then put it at, say, I don't know, 100. The window might be out of whack here, and graph it. But you can see the sharp climb in the values of y. And you can actually check your answers from this. Calculate the value at 10 days or at 20 days and see your value for what's happening with this scenario. Okay, I'm going to copy that and put it in our notes. So you can see a picture of this model and how it's evolving as the seconds go by. Now, exponential growth is widely used in population growth, finance, and even in the movies. And if you can think about when Ant-Man became giant Ant-Man, that was if you want to see the movie link, that's the YouTube link there, you can actually see Ant-Man changing to Giant Man. In this scene, exponential growth was used to change Ant-Man to Giant Ant-Man. Now, the general formula when we're discussing exponential growth in terms of uh, more, uh, the industry situation would be given by the formula uh, P is equal to P0 e to the power RT, using the base E or the number E for the the um, the calculations, and putting the growth rate as a power of that E. So here P0 is the initial amount, R is the growth rate, and percentage must be converted to decimal, and T is the time. So what I want to do here is bring in the work, a couple of the problems from the current homework, and show you what's happening with that. I believe this is so much stuff here. Courses. Let's bring that and embed it in here. I think it's in my material file. Okay, we're looking for the handout for 6.8. Here we go. And we're going to insert it as a printout and see what comes up here. So here's what the homework for this particular chapter. The size P of a certain population is equal to 900 insect population, 900 e to the power 0.30 t. What are the number of insects after t days? So when t is equal to 0, they're asking about the initial amount. Remember our formula here, P0 is equal to P is equal to P0. Let me write it on the side here. P is equal to P0 e to the power RT. And if we look at the equation we're given P is equal to 900 e to the power 0.03 t. So P0 is actually equal to 900 based on comparison with the formula. Then part B, the growth rate is 0.03, which is equal to 3%. After 10 days, so when t is equal to 10, P10 is equal to 900 e to the power 0.03 times 10. You would go to a calculator for that. (900) e to the power 0.03 times 10. And they want this answer rounded to the nearest whole number, so because we're talking about insects, so 1215 insects. When will the insect population reach 1350? So when would P reach 1350? So for this, you would have to set 1350 equals to 900 e to the power 0.03 t. divide both sides by 900. So you've got 1350 over 900 equals to E 0.03t. Then take logarithms on both sides. Then using the power rule, because we're trying to find t, okay? So logarithm 1350 over 900 equals to 0.03 t ln e. But ln e is equal to 1. So t is equal to logarithm 1350 divided by 900 divided by 0.03. In other words, if you wanted an algorithm to a formula to solve for time, time is equal to logarithm p divided by p0 over r. Okay. Now that goes into a calculator, and they're asking for one decimal place, so we're going to clear this, put it into a calculator. Logarithm 1350 divide by 900, close parenthesis, and then divide by 0.03. And we get that time as 13.5 days. Okay. I should box my answers here so you can see them. So the nice part of this is that they're asking you in part E, when will the insect population double? So part E, instead of going through the entire population, they're asking you when will P divided by P0, the initial, the population double from the original amount, or the initial amount. So when would P0 equal to 2? And we have an algorithm for time now. Time is equal to ln 2 over 0.03. Take this to 1 day, to one decimal place. So calculator. ln 2 divided by 0.03 to give 23.1 days. Okay, because this formula here that we created gave us what we needed to do to find this problem. Now, decay, radioactive decay occurs when instead of something growing exponentially, it's losing the amount instead of gaining the amount. Examples for those can be, say, your home smoke detectors that are made to last anywhere from 10 to 15 years. Smoke detectors in a house have small amounts of radioactive material that decay over time. And at the end of the life of the radioactive material, because the radioactive material is decaying at a certain rate every year, and at the end of that, once that radioactive material decomposes to a certain level, then you find that the smoke detector starts beeping uncontrollably, and you just have to take it outside and smash it with a hammer to get it to stop and replace it. That's the smoke detector's way of telling you that the radioactive material is no longer working. You can also look at things like, most of you probably too young to remember, say, Chernobyl, but Chernobyl was um, a disaster that occurred in the Ukraine, and what's happening is that for years people are not going to be able to go into that site, the because the radioactive material has not been decomposed, has not decayed to an acceptable level. I put in Chernobyl and how long until safe, and you can see that it will take anywhere from 20 years to several hundred years for it to be completely safe to people to enter Chernobyl without radioactive suits, or for the people to leave Chernobyl. So there's whole generations of families that are going to be stuck in Chernobyl that are not able to leave. We're not going to study anything so drastic. We're going to look at strontium is a radioactive material, and they gave us the formula here, where A0 is the initial amount present and A is the amount present at the time. Assuming that the scientist has a sample of 400 grams. So if we rework our little formula to A0 e to the power RT, and here they're telling us that A0, the initial amount, is 400. So this is 400 e to the power negative 0.0244t. First, they're asking us, what is the decay rate of strontium? That is a negative 0.0244 converted to percentage by multiplying by 100, so it's negative 2.44%. Negative because instead of doubling now, it's decaying over time. The amount that exists is getting smaller and smaller. How much strontium is left after 40 years? So A40 is 400 e to the power is negative 0.0244 times 40. Calculator. Round this to the nearest whole number. So let's put this in our calculator. 400 e to the power negative 0.0244 times 40 years. And we can see that it's approximately 151 grams. After 40 years, this radioactive substance still has a significant quantity left. When will the when will only 300 grams of strontium 90 be left? So think back to what we did in the last section where we said that time is equal to p logarithm, in the previous problem, logarithm p divided by p0 over the rate. And applied to our situation would be logarithm a divided by a0 over the rate. So time, they're asking when will 90 be left. So logarithm 90, let me make sure I have my numbers right here. I'm sorry, 300 grams. When would 300 grams be left? Yes, 300 grams. So logarithm 300 over the initial amount, which was 400, divided by the rate, which is negative 0.0244. So that's logarithm of 0.75, 3/4, divided by negative 0.0244. Calculator, logarithm 0.75 divided by negative 0.0244 to give approximately 11.8 years. And finally, what is the half-life? Half-life is when A divided by A0 is half. In other words, half of the initial amount, not double now, half. So time is logarithm half divided by negative 0.0244. Calculator. And to get oh, I forgot the negative sign on the denominator. So it will be positive 28.4 years. Okay. 28.4 years. Just in case you're wondering, all of these can be graphed. I'm going to graph this first equation here and show you the graph of it. This one, 900e to the power, and put it into our calculator and as a graph, and just to get a nice picture of what we're looking at. So this particular one was 900 e to the power 0.03x. And you probably want to mess with the window here a little bit. Remember, we had times in days, maybe 100 days is fine. Maybe our insect population was about 1350, so I don't know, maybe 5,000. Then you can see the steady climb of the graph. So perhaps after the question had asked, after 10 days, so second, calculate the value when x is equal to 10, and we can see it was approximately 1.1215. I'm going to capture that image and put it into our notes. for this problem here, so you can see the picture of it if you want to mess with that and see what's happening to it. Okay, that's it, guys. Please continue to work on your homework. I'm going to go ahead and end this